is given the next information. In this question you will be exploring the strategies required to solve a system of linear differential equations. Consider the system of linear differential equations of the form dx over dt is x minus y and dy over dt is ax plus y, where x, y, t are positive real numbers and a is a parameter. First, consider the case where a is 0. I 3 marks. By solving the differential equation dy over dt is y shows that y is a e to the power of t, where a is a constant. We can integrate it by separating variables, so it becomes dy over y is dt. Integrating both sides, we get ln of the absolute value of y is t plus some constant, and y becomes e to the power of t plus c, or e to the power of t multiplied by e to the power of some constant, and e to the power of some constant is another constant, so we can rewrite as required a to the power of a multiplied by e to the power of t. Next, 1 mark shows that dx over dt minus x is negative a multiplied by e to the power of t. From this we can see that dx over dt minus x is negative y, and y is this, so it becomes negative a e to the power of t as required. Next, 4 marks. Solve the differential equation in part aii. This differential equation to find x as a function of t. So we need to solve dx over dt minus x is negative a multiplied by e to the power of t. And we can see that it's of the form so that we can solve it by the method which is called by the integrating factor. And we need find an integrating factor firstly, and formula is given in a data booklet, and it is equal to e to the power of integral this expression in front of x, it's negative 1 dt, so it's e to the power of negative t. Then we multiply each term by the integrating factor and get e to the power of negative t dx over dt minus e to the power of negative t x is negative a e to the power of t multiplied by e to the power of negative t, it's just 1. Then, as usual, these two terms give d over dt the integrating factor multiplied by x and is negative a. Then, integrating both sides, we get e to the power of negative tx is integral of negative a dt, which is negative a t plus a constant. Hence, to get just x, we multiply each term by e to the power plus t and get that it becomes negative a t e to the power of t plus constant multiplied by e to the power of plus t, just constant multiplied by e to the power of t, and it's the required expression for x in terms of t. Next, now consider the case where a is negative 1 and bi 3 marks. By differentiating dy over dt is negative x plus y with respect to t shows that the second derivative of y is 2 dy dt, 3 marks. Dy dt is negative x plus y. It's this equation when a is negative 1. So let's differentiate the second derivative. Becomes negative dx over dt plus dy over dt. We need dy over dt only So we need dx over dt in terms of dy over dt. What can we use? We can use this, so it becomes negative x minus y, so negative x plus y, negative x plus y plus dy over dt, and we can see that negative x plus y is dy over dt, hence it's 2 multiplied by dy over dt as required. Next, by substituting capital Y is dy over dt, show that capital Y is b multiplied by e to the power of 2t, where b is a constant, 3 marks. Let's substitute into this, so it becomes y prime or dy over dt is 2y, and again applying a method by separating variables, it becomes dy over y is 2 dt, and integrating both sides we get a ln of the absolute value of capital Y is 2t plus constant, and hence y is e to the power of 2t plus a constant, or multiplied by e to the power of some constant, and it's another constant, let it be b, so it's b e to the power of 2t as required. Next, two marks, hence find y as a function of t. Y is b multiplied by e to the power of 2t, but capital Y it's dy over dt, and it's b e to the power of 2t, and hence dy is b e to the power of 2t dt, and integrating both sides we get that y is b over 2 e to the power of 2t plus some constant. Yes, it's correct. Next, hence shows that x is negative b over 2 e to the power of 2t plus some constant, 3 marks. We need x, and it is given dy over dt, so we can use dy over dt. A is negative 1, we consider negative x, plus y, so we can see that x is y minus dy over dt, so x is y minus dy over dt, and what is y? It's b over 2 e to the power of 2t plus the constant minus dy over dt, it's b e to the power of 2t, and we can see that it becomes negative b over 2 e to the power of 2t plus a constant as required. Next, now consider the case where a is negative 4. Ci 3 marks. Shows that the second derivative of y minus 2 dy over dt plus minus 3y is 0. 3 marks. So since a is -4, now dy over dt becomes -4x plus y. Dy over dt is -4x plus y, and let's differentiate it. The second derivative of y is -4 dx over dt plus dy over dt, and we can see we need to get rid of dx over dt. We need in terms of y only, so -4, and what is dx over dt? What can we use? We can use initial dx over dt is x minus y. It's x minus y plus dy over dt. It becomes y. Oh yes. Okay, so it becomes -4x plus 4y plus dy over dt. So we need x, and we need in terms of y the first the second derivatives only, so we can get x from this. So x is, or actually we need -4x. We can get -4x directly, and we can see that it is equal to dy over dt minus y. Hence it becomes dy over dt minus y plus 4y plus dy over dt, and move all terms to the left to get the second derivative. Dy over dt plus dy over dt is 2 dy over dt to the left, so minus 2 dy over dt, and 3y to the left, negative 3y is 0. Yes, and it is equal as required. Next, from previous cases, we might conjecture that the solution for this differential equation is y is f e to the power of lambda t. Lambda is rational and f is a constant. I 4 marks. Find the two values for lambda that satisfy this equation. So let's just substitute this expression for y. Let's find firstly the first derivative becomes f lambda e to the power lambda t, and the second derivative becomes f lambda squared e to the power lambda t, and substituting we get the second derivative. It becomes f lambda squared e to the power lambda t minus 2 f lambda e to the power lambda t minus 3y f e to the power lambda t is equal to 0, since e to the power of lambda t cannot be 0, and we can divide each term by f. Hence we get the next, that lambda squared minus lambda minus 3 should be equal to 0. 2 lambda squared minus 2 lambda minus 3 is equal to 0, and roots are -1 and 3. Just applying sum and product rule. Sum is 2, product is -3. Next, let the two values found in part CII be lambda1 and lambda2. Next, for marks, verify that y is f e to the power of lambda1 t plus g e to the power of lambda 2 t is a solution to the differential equation in CI, it's this one, where g is the constant. So we need just substitute this expression for y into this equation and show that it is true. So let's find firstly the first derivative becomes, or actually we can substitute our values for lambda, so it becomes y is f e to the power of negative t plus g e to the power of 3t, or 3t, and the first derivative becomes negative f e to the power of negative t plus 3g e to the power of 3t, and the second derivative becomes again minus, so plus f e to the power of negative t plus 9g e to the power of 3t, and substituting we get the second derivative, so f e to the power of negative t plus 9g e to the power of 3t minus 2 the first derivative, minus 2 the first derivative, it's negative f e to negative t plus 3g e to the power of 3t, and minus 3y, minus 3yf e to negative t plus g e to the power of 3t is, and we need to show that it is equal to the right hand side, that it is equal to 0 as required. So let's just simplify and add like terms, so it becomes f e to the power of negative t plus 9g e to the power of 3t plus 2f e to negative t minus 6g e to 3t minus 3f e to negative t and minus 3g e to 3t. Let's check. 9 plus 2f minus 6g minus 3f and minus 3g, and it is equal to, we can see 1 plus 2 minus 3 is 0, 9 minus 6 minus 3 it's 0. So it's clear that it's 0, so it is equal to the right hand side as required. And that's all for this question.